Is there life in the universe? It doesn't get deeper than this, does it? And yet, why do we care about that? In the very small chance that there is other life in the universe, we have even less chance to discover it, talk to it, and meet it. So, why do we care? Well, it may surprise you, but Bayesian statistics helps us think about these astronomical and, dare I say, philosophical topics, as my guest, David Kipping, will brilliantly explain in this episode. David is an Associate Professor of Astronomy at Columbia University, where he leads the Cool Worlds Lab. I know, the name is awesome. His team's research spans exoplanet discovery and characterization, the search for life in the universe, and developing novel approaches to our exploration of the cosmos. David also teaches astrostatistics, and his contributions to Bayesian statistics span astrobiology to exoplanet detection. He also hosts the Cool Worlds YouTube channel with over 500,000 subscribers that discusses his team's work and broader topics within the field. Cool words, cool guests, cool episode. This is Learning Bayesian Statistics, episode 67, recorded August 10, 2022. Welcome to Learning Bayesian Statistics, a fortnightly podcast on Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the podcast, learnbayestats.com is la place to be. Show notes, becoming a corporate sponsor, supporting LBS on Patreon, unlocking Bayesian merch, everything is in there. That's learnbayestats.com. If with all that info, a Bayesian model is still resisting you, or if you find my voice especially smooth and want me to come and teach Bayesian stats in your company, then reach out at alex.andorra@pymc-labs.io or book a call with me at learnbayestats.com. Thanks a lot, folks, and best Bayesian wishes to you all.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations.
What's a Bayesian? Is someone who cares about evidence and doesn't jump to assumptions based on intuitions and prejudice. A Bayesian makes predictions on the best available info and adjusts the probability, cause every belief is provisional. And when I kick a flow, mostly I'm watching eyes widen, maybe cause my likeness lowers expectations of tight rhyming. How would I know unless I'm rhyming in front of a bunch of blind men dropping placebo-controlled science like I'm Richard Feynman?
Hello, my dear Bayesians. It's not only David's lab that's cool, but also my dear Patreon supporters. This time, I want to warmly thank David Haas and Robert Jolkin, who just joined the Good Bayesian and Full Posterior tiers, respectively. Welcome to the community, guys. And David, make sure to send a picture when you get your exclusive LBS merch. Okay, now let's get both nerdy and philosophical with David Kipping. David Kipping, welcome to Learning Bayesian Statistics.
It's a real pleasure to be here.
Yeah, thank you. I'm so happy to have you on the show. The topics that we have today on the board are awesome, so can't wait to dive into that. But again, thank you to the podcast listeners for sending me guest recommendations, because you were actually recommended to me by one of the listeners. So thank you very much.
Oh, that's so kind. Thanks for recommending me, guys. Yeah.
Yeah, very kind listeners. They are the best, of course.
They're very wise.
It's a bit like my children, I don't know, I don't have any children yet, but I feel like it's the same kind of love. But yeah, so thank you very much, folks. Keep the suggestions going, because I love that serendipity, so that's awesome. And before we dive into the core of the episode, as usual, I'd like to talk a bit about you in particular, David. So first, maybe for the listeners who don't know you, could you define the work that you're doing nowadays and also the topics that you are particularly interested in?
Yeah, so I teach astronomy at Columbia University, and I have a research team there called the Cool Worlds Lab. And when people hear that name, Cool Worlds, they think it's like dope planets or something. And that's really not what we intended. It's kind of a play on words, but we're interested in planets at long orbital periods around their stars. And that's just because they're kind of rare because of lots of detection biases that actually affect the way we look for planets. So very few of them are at long periods, despite the fact probably in the universe there are lots of them out there. And those planets are kind of special because they're far enough from their star that there could be liquid water on their surfaces if they're rocky, so the potential for life. So that's, of course, of great interest to us. But also, I'm probably most well known for my work on looking for moons around these planets. And if you have a planet that's too close to the star, then the tidal forces of the star and the gravitational influence of the star basically rip off those moons in pretty short order. So Cool Worlds has always been interesting for those two primary reasons. There's just a lot of interesting stuff happening out there. And then we also have a YouTube channel after the namesake of the group, which I feel like I'm much more well known for now than the research, strangely enough. And so, yeah, there we just started out just putting videos out about research papers we were writing, and it's been growing over the years. And we do videos on other topics as well to do with space and life in the universe. And it's, for whatever reason, it's clicked, and we're doing pretty well there. I think we just crossed 500,000 subscribers about a month ago. So
nice.
Yeah, it's amazing.
Yeah. Congrats on that. I know how content creation is both a challenge and a joy. So
you're in it. Yeah, this is it.
yeah. That's super cool. And so happy to see so many people interested in those topics, and just seeing science education being popular in general is always something that's dear to my heart. So that's cool. It's pretty incredible how YouTube can be both the worst and the best of the content that are out there.
Yeah, I kind of think in a way, YouTube and podcasts, they've eclipsed what you can find through mainstream television when it comes to educational content. I mean, if you go onto Netflix or Amazon Prime, there's very little, and you can find stuff that's of much higher quality. You have to look for it and have to find those channels, but they're out there and they're producing really stellar content.
Yeah. And well done for that pun, by the way. Impressive. Completely agree. It's like finding the first few channels is hard, and then the YouTube algorithm helps you.
Yeah.
If you have the first few channels through recommendations by some friends, or, we all have a nerdy friend who is into astrophysics or astronomy. So just ask them and they will tell you what to look for, and then you can go into that. There is the PBS Spacetime channel. I really love it too. I think I understand 10% of what they are saying in each episode.
Yeah, that's a common feeling about that channel. I love it, but they go it's amazing given how high level they go, that they consistently have millions of viewers on their videos.
Yeah.
And I mean, of course, there's a whole diverse, I think people just like seeing how far can it go almost. And it's presented, of course, so professionally, and the graphics are beautiful. So it's kind of entertaining just to watch it. And hopefully you can learn something. A lot of these topics that they talk about, the first time you encounter it, it is quite mystifying. But there's, by the 10th time you've heard about cosmology and general relativity and things, a little bit more starts to creep in at some kind, your background subconscious is doing some work there and it's connecting dots for you. So sometimes you just have to kind of stick with that kind of content, and it does eventually work for you.
Yeah, no, I completely agree. And I mean, also there is partly a masochist part of my brain, I think, which loves, not understanding and being oh my God, this is so much more complex than what I imagined. But that's super cool because that means I have so much to learn and to understand. So in a way, I like that feeling. Also, it feels efficient.
Yeah, I know the feeling. And I think a lot of my viewers feel that way when I talk about Bayesian statistics, actually. So it's not a topic that I talk a lot about, but I've done probably 5 or 6 videos where I've brought it in. And whenever I do, I feel I see in the comments that people are that bit I just had to block out almost because it was just too much. But yeah, my hope is that if I keep building it in, just keep trying to explain it and keep working at it, I really think, I'm sure you agree, Bayesian statistics is pretty intuitive actually once you get your head around it. So it's just the way it was taught to me at school was so confusing. I had no idea what was going on when I learned Bayesian statistics at high school. But then once I started to actually dive into it myself, it made more sense. And so I tried to transmit that in the videos as to that it is an intuitive thing actually that we have a lot of experience with in our own lives. So it can scare people off, those kinds of technical topics, including Bayesian statistics, but it's worth it to try and get them in.
Yeah, couldn't agree more. So that's also the good thing of that kind of, niche audience. That is definitely the audience of the podcast, because that's also why I love my listeners, is that they don't shy away from technical topics. And sometimes I have extremely statistically technical episodes, and they tend to be also among the most popular. So it's really interesting. It's not only the applied episodes like the one we're doing right now. It's also like deep statistical episodes. People love them too, and that's super cool. So let's feed that thirst of your audience and so bring them to me. They will have everything they need for Bayesian stats.
Sure, yeah.
And actually, so you touched a bit on that, so let's talk about it now, because something I always ask my guests is, how did you encounter Bayesian methods the first time, and why were they interesting to you?
Yeah, I think the first time was at A-level mathematics in the UK. We had a stats teacher there, and it was confusing. I remember all of us felt confused. I think I did pretty well. It's just like learning the rules, but I didn't really understand what I was doing with the techniques. And then I think because of that, I sort of convinced myself I wasn't good at statistics, even though actually I'm sure I got an A in that. I just convinced myself I only just got an A. I felt like in my head, like I had to really work for that one. So I focused on physics at college, went to Cambridge in the UK, and I did some mathematics, but mostly more kind of applied maths, not so much on the statistics side. And then eventually, I think it was only really when I started research that I got into statistics seriously. And so I started this project, as I mentioned, looking for exomoons, is sort of the thing I'm most well known for. And I've always been the sort of person that likes to work in small teams rather than big teams. And so I like to, they also like introverts like to have a few really close relationships, whereas extroverts like to have lots of looser relationships. I'm probably more on the former side. And so I've always liked working in small teams. But as a consequence of that, we didn't really have anyone who knew statistics. And so I sort of took that on like, okay, I'm going to do that. And I think the very first breakthrough I had that convinced myself I could do it, I remember I was in Brighton in my girlfriend, now wife's apartment at the time. And I had told myself, I'm going to learn how to do an MCMC. I'd like seen this phrase MCMC in loads of exoplanet papers, and I could see it was growing in importance. And I didn't like the fact I didn't really understand what it was doing. And so I thought, I'm just going to code up my own one, follow the recipe, try and figure this out. And I sat all day on her sofa and just coded it up. And of course, it's not that hard, as you probably know, to write an MCMC. It's not that many lines of code, I should say, to write an MCMC. You can do it almost in like one line if you're really efficient. It took me maybe a bit more than that. But when I got it going, it was the best feeling. And that's when I started to gain my first intuition about what's really going on. And so I started this journey of applied, mostly regression, sort of fitting models. I eventually switched over to a nested sampling approach rather than MCMC methods. And that was mostly through a collaboration at Cambridge. So John Skilling, who really invented nested sampling, he was mentoring a student, Farhan Feroz at the time at Cambridge, who was writing this package called Multinest. And it was meant to be a multimodal implementation of the nested sampling algorithm. So I'm not sure, maybe I should just say for those who aren't sure what nested sampling is, to explain the difference quickly. So nested sampling, the difference is, I always say that MCMC is kind of like an inside out. So it starts from a single guess what it thinks the parameters of a model should be. And then it makes a jump and it tries to evaluate, is that guess, better or worse? And it'll accept or reject it with some kind of rule, typically the metropolis rule. Whereas with nested sampling, it really starts from the outside in. So it kind of throws, let's say, 1,000 called live points over the entire prior volume. And then it evaluates the likelihood of all of them. And instead of trying to just find the region of highest likelihood, which is more or less what MCMC is doing, it tries to draw a contour of constant iso likelihood, or really iso posterior probability across the entire parameter volume. And then once it's found, it iterates on that. Once it's found that contour, it shrinks that box down a little bit by an even interval, and it keeps shrinking these contours down. And so within each contour, the posterior probability and the volume. And so you can actually turn the Bayesian evidence integral, the marginal likelihood as it's sometimes known, from an integral into a sum. It's just going to be basically the trapezoidal rule, integration rule of the delta volumes multiplied by the contour heights. And so you can evaluate the marginal likelihood, which is something which is normally completely off limits to MCMC, unless you're doing like parallel tempering or something kind of sophisticated on the back end. But this is a much more efficient approach. Nested sampling really is designed pretty much specifically for that goal where you want to measure marginal likelihoods. And so to the more casual listener, what that really means is if you want to compare models. So in my case, that's critical. I want to do a planet plus a moon model, and I want to compare that to a planet model. And of course, if I just do likelihood, I'm always going to get a better likelihood by including the moon. It's a nested model, which means I could always set the moon mass to be 0, and it would essentially recover the planet by itself. So that's a nested model. And whenever you have a nested model, it's guaranteed to give you a better likelihood. You can't get a worse. Like if you go from a cubic fit to a quadratic fit, you have to get a better fit. There's no alternative. But that doesn't mean you should accept the fit, because it might not be, via Occam's razor, it might not be very efficient with how, the improvement in the likelihood might not really justify the extra degree of freedom you added. So formally, you compare models with the marginal likelihood to do this. And that's where nested sampling came in. I know this is kind of working around in this story a little bit, but yeah, I think once I started collaborating with John Skilling, just to cut the story there for a moment, that's when I started to get a bit deeper into really understanding how all this works.
Well, perfect. That also answers the question, like, why did they stick with you in a sense, and like, why was it interesting? And I think you're one of the first guests to answer that question by basically saying the algorithm was the thing you were most interested in, more than like the philosophy or something like that.
At the time, yeah. I think that has evolved, actually. But yeah, at the time, and it wasn't really, actually, to be fair, it wasn't actually the algorithm, it was the function of the algorithm. I was just interested in looking for moons back then. Really. That was my primary goal. I just wanted to find moons, and I knew this was the way to do it. And so it was just a case of chasing the most rigorous statistical approach I could. And having met with John and Farhan, I knew that was the direction to go. After that, I've come to, think more deeply about Bayesian statistics in a more analytic way, away from regression. And so some of my more recent work has gone into the priors a lot. So I kind of love small data, actually. That's kind of my thing. Not big data. Big data, I feel like it's too easy. The data tells you the answer. You don't have to work too hard. But when you're small data, the priors have a much bigger influence. And so I really like those problems. So I've written papers on so-called like black swan events in astronomy, like Oumuamua, which was this famous interstellar asteroid that passed through the solar system. Seems like a one-off. So from that one-off, what can you infer about the rate of such events? There's similar examples would be like the WOW signal. The WOW signal was this supposed alien transmission from 1977, only happened once. And so if you assume some kind of repeating beacon, how consistent is the hypothesis of repeating beacon with this one-off event? So again, with one data point, the way you construct your formalism for that problem has a huge bearing in the priors. And so I really got into those. And probably the one I'm most passionate about has been the origin of life, the timing of when life emerged. And so I've written papers on that topic as well, thinking about what does that really does a lot of people say life starts early, therefore life is everywhere in the universe. And so I really wanted to take a Bayesian hammer to that and ask that question more rigorously.
Oh yeah, super cool. Feel free to talk more about that right now. And we need definitely the things you just talked about. If you can add references in the show notes.
Yeah.
For papers, books, videos, things like that. Yeah, definitely. That'd be super cool. And yeah, actually, I wanted to ask you about an example from your work that illustrates both what you do and how Bayesian stats are helpful there. So seems like the priors and timing of life seems perfectly appropriate to talk about that.
Yeah, so that was an interesting question, and it's been tackled a few times in the literature before. And I guess I was getting kind of frustrated because I kept seeing like Nature papers and science papers that would revise the date of when life emerged on Earth. They'd found some new evidence. And there was almost always a commentary attached to that would say, this therefore proves that life is everywhere. And I was thinking, it's not obvious to me that's true. And the reason why it's not obvious that it's true is because of selection bias, survivorship bias. So one thing that probably will surprise a lot of people when they first learn this, probably a lot of people know that life started pretty quickly in Earth's history. So we're currently about 4.5 billion years old as a planet. And life seems to have emerged almost as soon as the oceans formed, or very soon after the oceans formed. So sort of 300 million years is the very earliest estimates. The most conservative would put it at about just under 1 billion years. If you want actual fossils, you have to go to about 1 billion years. If you're willing to use sort of other or more indirect methods, you can go back to 300 million.
So like more or less life appeared like in the first 20% of the timeline, basically.
Yeah. In fact, possibly even quicker than that. And which is an important part of the problem, actually. We don't know when life started. We don't know when life appeared by. Just because you see a fossil doesn't mean that was the very first living thing that ever lived. That presumably there was something before that didn't leave a fossil. And so that actually affects the formalism quite significantly, that you only have really an upper limit on when life arrived. But the other thing that might surprise people is that there's an upper limit for when the Earth will become uninhabitable. And that's quite soon. It's in less than 1 billion years. So the sun will probably gobble up the Earth in about 5 billion years. So that's clearly game over at that point. But actually way before then, the Earth will probably become uninhabitable to complex multicellular life such as ourselves, things capable of technology and thinking and statistics and abstract thought. All of that will probably go within about 0.9 billion years. And so this is largely driven by the sun's increasing luminosity. So the sun has increased in luminosity by about 30% since 4.5 billion years ago, and it continues to increase in luminosity. And the Earth is already actually pretty close to the inner edge of what we'd call the habitable zone. It's kind of teetering on the edge in most of the models. Doesn't take much. That's why we're so worried about climate change. It doesn't take much to push the Earth over. What basically happens as the sun warms up, or I was trying to say that, as the sun's luminosity increases, is a more accurate way of saying it. It increases the rate of weathering on the Earth. So sort of things like the evaporation cycles and precipitation. And whenever you get precipitation, that dissolves carbon dioxide into carbonic acid in the raindrops that then filters down into the Earth and forms limestones and things like this, and calcifies, and we basically lock up all that CO2 into rock in the Earth. So this seems great in a modern time because we're trying to get rid of CO2 out of the atmosphere, and this is what's happening. The Earth will lose CO2 in the long run. This is called the long carbon cycle, but it happens over tens of millions of years. But the problem is this will actually probably kill us in the end. As the weathering increases so much, CO2 levels will drop below about 10 ppm in about 0.9 billion years. It's currently obviously 400, should be about 300 naturally. But once it goes below 10, photosynthesis stops. It's just not possible to photosynthesize below 10 ppm. And so all the plant life dies and the food chain collapses. So that's kind of interesting from a physics perspective, coming back to this, because it's kind of surprising then that we seem to have emerged almost in the last chapter, right? So we emerged in the last chapter. And that's curious then, because if it takes, let's say, 4 billion years for intelligent life to evolve, which it happened on Earth, and that's a typical number, that's the typical timescale it takes, or indeed it could be a little bit longer than that in some cases, then that means that life really has to start quickly. Otherwise, we wouldn't. If life started in, let's say, at 1.5 billion years after the Earth was formed, there wouldn't be enough time for evolution to get to us before the sun would make the Earth uninhabitable. So the early emergence of life isn't interesting. It's a necessity to our existence. And so only beings such as ourselves, which are capable of abstract thought, would all find themselves on planets where life started quickly because it had to be true, else there wouldn't be time for them to have evolved, assuming they live around sort of similar sun-like stars. Obviously, different stars have different lifetimes, but there's good reasons to think that sun-like stars are particularly important and perhaps the place to look for life in the universe. And so that's a really important selection bias that was basically totally ignored in a lot of previous work. And so I got really inspired into this. There was a kind of an attempt at taking this into a Bayesian world, very famous paper in the field of astrobiology, at least, by Dave Spiegel and Ed Turner from Princeton. And they basically took this Bayesian problem, they kind of formulated this problem of how long does it take life to emerge using a Poisson process, they assumed. And they just had really one parameter they were trying to infer, and that was the rate of abiogenesis. And their one data point, well, I suppose they had two data points, I should say, was when life appears to have emerged by on the Earth, which is that sort of very early number, and how long do we have until it had to have emerged by that point, else we wouldn't be here to talk about it. So they were just trying to infer it. And that seems like a straightforward problem, except for the fact, and my criticism of that paper was that they had to fix the evolution time for intelligent life, which is the other related topic here. So we just talked about that. If it takes 4 billion years for us to evolve, for things like us to evolve, then you wouldn't really put too much weight in the fact life started early, right? You'd be like, well, it kind of has to start early. That's just a necessity. And so you wouldn't really be able to infer much about it. But if you instead said that, no, intelligent life can start really quick within like 1 billion or 2 billion years, we're just unusual starting as late as we did, then you would say, well, actually, intelligent, simple life could have started much later. If it only takes 1 billion years for intelligent life to evolve, you could have simple life starting now and still have time to get to intelligent life before the sun runs out. So they're degenerate with each other. And so that was really my criticism. You can't really consider one in isolation. The timescale of evolution for intelligent life and the timescale for life emerging are interrelated, not in a physical sense, perhaps to some degree in a physical sense, but I mean because of the bias that comes into this problem, the survivorship bias. That's why they're so intimately related to each other. And so my paper basically expanded that model and let both of those be parameters that we were trying to infer. So that was the first really big change that I made. And then the second one was the priors. And the priors was another big problem. In that first paper, they showed that if you change the prior between reasonable objective priors for the rate of abiogenesis, you get wildly different answers. And so most people concluded from that there's nothing we can learn from the early emergence of life. It's a meaningless data point. Is you change the prior and you get a completely different posterior. And so I kind of found a little trick around that to show that the priors don't matter and you can actually sort of cancel them out. And so the way we did this was to take limits of our final likelihood function. And so we considered 4 extreme cases. So there's basically 4 possibilities. There's one is that the rate of abiogenesis, how long it takes life to get going, is a very, very rapid process, or it's a very slow process. So there's 2 possibilities. And by rapid and slow, I mean compared to the lifetime of the planet. It's either something that happens in 1 million years or 2 million years typically, or something that happens in like 100 billion years typically. It'd be pretty odd if it was fine-tuned to exactly the time scale. There's no real reason why it'd be fine-tuned to exactly the time scale of the lifetime of a planet. So it's probably somewhere in those 2 regimes. And similarly, you can do the same for intelligent life. You can say it's probably a very quick process or a very slow process. It's one of those 2. So there's kind of your rare intelligence and intelligent life everywhere scenarios. So you have these 4 scenarios and you can basically take the limit of your function. And when you do that, you can use this trick called the Savage-Dickey ratio. So this is a cool trick for anyone who's interested in Bayesian model selection. The Savage-Dickey ratio allows you to calculate the model evidence, the Bayesian model evidence, just from a posterior. So you can avoid having to go through things like multinest or doing this integral more formally by hand, which is kind of clever. And the way it works is it's essentially, I'm not going to go through the proof, of course, in the podcast, but if you take on trust there, I'll put the link in the notes afterwards. It essentially takes the posterior distribution and it evaluates the density of it at the point where the models overlap for 2 nested models. So a simple case would be like for my exomoon problem, the moon mass would be 0, would correspond to just a planet by itself. And so I just plot my posterior distribution of what the mass of the moon is. And it has a certain, maybe it peaks at say 0.1 Earth masses, let's say. But it's like a little Gaussian. And so that tail drops off and then it has some certain finite height at 0. There's some finite probability of it being a 0 mass moon. And so you just basically compare the height or the density really at 0 compared to the density of your prior. And that ratio is the Bayes factor between those 2 models. And that's the Savage-Dickey theorem. So it's a really beautiful theorem. Only works for nested models like that. And so in our case, for the life problem, the nested model is that basically you're comparing to some generic hypothesis that life and intelligent life don't have any extreme behavior in terms of their fairly typical values. And you're comparing that generic hypothesis to this extreme case where I'm evaluating it in the limit of no, abiogenesis is basically an infinitesimal process. And so you can get a Bayes factor between a limiting case and the generic model. And then you do that for all 4 corners. And of course, the generic model is kind of a meaningless concept in a way. And so then you can just cancel it out and compare the 4 corners to each other. And so that's what I did in the paper. And so then you can show, in conclusion, that actually, despite all of those selection biases, it really does look like there is some good news for life in the universe. That we found 3-to-1 odds the Bayes factor was 3-1 between a common life scenario and a rare life scenario. And because of this Savage Dickey, actually, as I said, the priors cancel out. So actually, you can change the prior. You can say for the rate of abiogenesis, I want to use a uniform prior, a log uniform prior, whatever you want to use. It doesn't matter. Everyone would agree the Bayes factor would be 3-1. And that's really by construction what a Bayes factor is, right? Because a Bayes factor is basically a likelihood ratio. So that's why the prior's in there at a deeper level. And so you might argue about what the model ratio should be, which is that if you really want an odds ratio, it's the Bayes factor multiplied by the model odds ratio. We don't know what to do for the model odds ratio, but at least the Bayes factor, we can say 3-1 odds that life really did appear to start quickly. And therefore that should happen. It's not just a consequence of selection bias. It genuinely should have happened with or without us, whether we're here or not. That seems to be the case. I can't give you a number of how fast it happened, but I can give you that model odds. And then when we do it for intelligent life, we got 3-2 odds in favor of rare intelligence. So and that's really driven by the fact we occur so late in the timeline, as I said. It's kind of odd that we occur as late as we do. But 3-2, 3-1 is already pretty soft odds. Yeah, 3-2 is 1.5. I wouldn't really put any weight in that because the prior is 1-1 essentially. So you've shifted the needle from 1-1 to 1.5-1. So I think for intelligent life, I always say my paper basically has no conclusion. It really doesn't know what's going on with that. There's not enough data to pin that down. But for life, it is at 3-1, which is interesting. And if you use the most optimistic evidences for life on Earth, it pulls down to 9-1. Which really should give us some hope then that there is life out there in the universe.
Yeah. Well, first, thank you for that long monologue.
I'm sorry. Yeah.
Must have been exhausting. No, it was perfect. I was hooked. Yeah, super interesting. So many things we could take the conversations to. So something I'm wondering is, all these discussions, though, do they rest on the assumption that intelligent life is basically our form of intelligence? Or do you also take into account that maybe there could be more intelligent versions of us which figure out things way faster than us, like medicine, agriculture, things like that helped us to make leaps and bounds very fast, and basically civilization which would leapfrog on what we did but would do that way, way faster, and so would attain a point of advancement way faster than us in comparison. Do you take those kind of things into account?
Yeah, I think a way of kind of asking your question, it's a question I've had a lot with this paper, is, there is this conditional, if we're going back to the Bayesian side of it, there is a conditional here, and that's the conditional is that given that we exist, or given that something like us exists. And so the question is, define that conditional more explicitly, I think is another way of asking your question. What does that really mean, something like us? And so in the paper, I've thought about this a lot. I'm still not sure if I'm totally satisfied with my answer to this, but in the paper, I said it's a ensemble, a society, a being that is capable of doing basically paleontology or micropaleontology of figuring out these dates. You can't do this analysis unless you're able to determine the dates. I've also doing astronomy or astrophysics, so they know when you have a sense as to when. I guess that's not so critical, but they're scientifically literate and they're able to determine these things about when the lifetime of their star, and they're able to do statistics. Because obviously the conditional is really the paper itself. It's kind of a weird cogito ergo sum type thing, but the paper itself is the conditional. And so it has to be possible that another civilization could have written that type of paper. And so for all civilizations that could write a paper like that paper, amongst them, that is the survivorship bias that we're essentially applying. And so it could be much further ahead of us in terms of their development, but that's sort of the minimum bar of what they're capable of. And I don't think there's any clear upper bound as to how advanced or sophisticated they could be. But obviously they might have more data than us. I mean, if you're more advanced, you might, who knows, be able to have a time machine and just go back and observe the date when life started, and then you're fine, right? So obviously they could have more data than us, but with the data we have right now, I think that's a pretty good definition of the conditional.
Yeah, and like if they figure out things faster, also like basically they need math, physics, and scientific reasoning. But you also need to be fed. You need like people who are able to specialize to write those kind of papers, because they can rely on people who like can harvest fields for them and so on. So it's like, yeah, you need a pretty advanced civilization. And so, yeah, you can imagine that maybe a civilization does that faster. Also, maybe the fact that they do that so much faster means that also it changed their outlook, because then it could be like, well, we're not appearing at the last chapter of Earth, right? We appeared way before. And also, like, because of the expansion of the universe, maybe they observed the sky way before we did that consistently. And so maybe they figured more stuff out than us because it's easier to spot things in the sky before than right now. So it could change a lot of things.
Well, we get into a lot of Fermi paradox stuff here, which is great. I mean, that's really my other hat is technosignatures and the search for life in the universe. And of course, these are things that we debate endlessly in the community. And it's a lot of fun to try and wrap around your head around what other civilizations' behaviors and activities and capabilities might ultimately be.
Yeah, because then you can also expand the question to, also we're talking about our form of life, which is the only one we know, but maybe there are other forms of life which are not carbon-based and need oxygen and need water. So that's the kind of thing here it's like almost a known unknown, right? It's just like, yeah, maybe, but how do you study that? It's super hard.
Yeah, I mean, I've been thinking about some of this stuff a lot recently. It's kind of like a draft on my computer, but I keep dropping in and then picking it up again. And it's a really hard problem. And it's thinking about, with the search for life, what is your completeness? Might be one way of saying it. What is your true positive rate? So as I said, there could be life out there, which is so different from us, we don't recognize it. I mean, there could even be another branch of life on Earth. It's called the shadow biosphere hypothesis, that we just don't, it's on our fingertips and we just cannot detect it. But it's basically a completely separate origin of life that happened on Earth. It's possible. And so that true positive rate could be quite small, and it's very difficult to quantify what that true positive rate might actually be. And on the other hand, you have your false positive rate. And that, again, is very challenging to pin down. So by search for oxygen as a signature of life, obviously plants make oxygen through photosynthesis. Oxygen is a very reactive molecule. It shouldn't really be in an atmosphere. By all rights, it shouldn't be there. Something has to really be producing it, because it just oxidizes stuff. So all the plants die, within 1 million years, the oxygen on this planet would be gone. It just reacts fairly quickly on geological timescales. And so we're looking for oxygen as a possible sign of life. But then other people have shown recently, well, there's other ways of making oxygen. UV rays, when they hit the upper atmosphere, if there's a lot of water in the atmosphere, it could break apart the water and photolyze it. And so you then have free oxygen, and it splits the water up into hydrogen and oxygen. The hydrogen is very light, and so the hydrogen could escape into space. Basically, Earth has already lost all of its hydrogen pretty much because of that process. And so then you'd just be left with oxygen, which would then appear as a biosignature, even though there's no life involved. And so that's one example of a known process we can think of that could trick us. But then what about all the other geological processes? I mean, there's a big case on Mars, right? In Mars, there's evidence of methane, growing evidence for methane. And so that on Earth is largely a product of life, cows burping and farting and things. But we don't really think that's what's going on Mars necessarily. There could be some reservoir or some geological processes we don't quite understand that are going on underneath the surface that are producing methane. And so one of the great challenges with the search for life is, how do you interpret an experiment, and again, in a sort of rigorous statistical Bayesian way, if you can't even quantify your true positive rate or your false positive rate? You'd no idea what even to put in for those numbers. How do you interpret? If I give you 100 experiments and I say 60 of them were successful, but I have no idea what the true positive rate and I have no idea what the false positive rate is, it's almost impossible to make any sense of that number. And so this is kind of a fundamental problem. I don't know how we're going to, at the moment, really make progress unless you have something that's really unambiguous, in which case you can say the false positive rate is 0. So an example of that would be an alien transmission that's like a prime number sequence. It's just like, we are here, or we land on the White House lawn, and they come out, they shake hands, and the false positive rate there is pretty damn low. It still could, I suppose, be some kind of scheme to try and trick us all, but you'd think that would be a dramatic hoax to pull that off. But in that case, you'd say the false positive rate is almost certainly very small. But when we're doing telescope observations, we don't have access to that assurance. And so this is a big problem. It's got me worried about our search for life a lot.
Yeah, I can guess that. time is flying by and I want to ask you about other things. So let me ask you like kind of a meta question on that project that you just talked about. And so first, we definitely need those papers and references in the show notes. And so my question is like maybe which difficulties did you encounter with this project and what did you learn from them that will help you for future research?
Yeah, I think mostly I've thought very intensely about priors, as I said, in these projects. And that's because this problem is a very data-starved case. But I think by focusing on the influence of priors very carefully, it's taught me a lot about what should go into the prior and what shouldn't, and how to formulate your priors, and the influence they also have on problems that have maybe more data in hand as well, going back to those sorts of problems. So to sort of give you some greater context there, I mean, one of the things it might put into your prior is if I was looking for trying to measure the radius of a planet, let's say, then I might want to have a prior that was the intrinsic radii of planets in the universe. So let's say we'd gone out there and we had a perfect telescope and we'd somehow measured all the radii of all the planets in the universe. And they looked like a beautiful Gaussian sat at, let's say, 4 times the radius of the Earth, Neptune. Neptune is the most common type of planet in the universe. There's some Earths, there's some Jupiters. And so if you had that would be your prior. When you're trying to measure the radius of a new planet, you would take that intrinsic distribution, you'd use it as your prior because it is a planet and it belongs to this population of similar type planets. So that's one, and that's kind of a chicken and egg problem, right? Because how can you know what the true distribution of all the planets are before you've measured it? So that again remains one of the sort of challenges we're grappling with and we've been approaching with methods like hierarchical Bayesian modeling, which sort of fit everything at once. So you can actually fit the prior and your individual population parameters all at once in hierarchical models. So that's been sort of growing in my field and in my own work as well a lot. But then the other prior you might build in is the detection bias. And so I should say observational bias. Let me say that, the observational bias. And the observational bias could actually have 2 different forms. One is with planets. The most common way we look for planets is the so-called transit method, and that's when the planet passes in front of the star. And that's really only going to happen with the correct geometry. And so there is a bias then towards basically planets which are close to the star. They have to have the right geometry. And it turns out, if you think about it really hard, there's also going to be a slight geometric bias towards bigger planets. If I want to get 2 things to block each other out, the bigger the planet is, the easier it's going to be to have some kind of partial alignment between the 2 disks on the sky. And so there was actually a geometric bias towards finding bigger planets. And then on top of that, there's a completely other type of observational bias, which is detection bias. And that is that my telescope isn't perfect. It has some noise floor. And so maybe I can't detect as small of a planet as I'd really like to. And so you're going to then be biased towards, for any given star with some arbitrary brightness, finding a larger planet than you would really like, than the intrinsic distribution might imply. And so that's been a challenge. It's like, how do you fold in these 3 fairly complicated biases? When is it appropriate to build them in? What are your conditionals? And so in my team, we've been working quite hard on formulating analytic priors that the community can use for those sorts of problems. And I just get a big kick out of that kind of stuff. It's like being Sherlock Holmes at a crime scene when you find a planet. It's not like in physics where you can go to the lab and you can just repeat the experiment over and over again. Oh, you want to measure the electron mass a bit better? Just do the experiment 10 more times. We can't do that. These transits happen infrequently, and we can't make the planet transit again. We just have to wait sometimes like 5 years for it to transit again. So you're kind of stuck with the data you've got, and it's like being at a crime scene. You can't add new clues. There's just the clues that are there in the room, and you have to do your best to extract as much information as you can out of it. And so, when we're developing these better priors, it's almost like we're developing the forensic techniques. We're improving those forensic techniques to extract just a few more strands of DNA out of that hair. And so I do get kind of a kick out of taking limited finite data, which is really the fundamental premise of Bayesian inference, and trying to maximize how much you can learn about whatever it is you're studying from it.
Yeah, okay. I see what you mean. So in general, I'm wondering, right now, in your field, what would you say the biggest question is right now? Like the one question that you'd like the answer to before you die, let's say.
Is there life in the universe? I'd say it's probably, it's sometimes said that there are two types of astronomers. There are those who want to know how the universe works, the mechanics of it. How does a black hole work? What caused the Big Bang? Why is the universe expanding? And I'm definitely fascinated by those questions. I think we all are. But the other type of astronomer is more driven by the question, is there someone else out there? Are we alone in the universe? And that also has huge cosmological implications if it's true. And so that's the question that's driven me more in my career, as I think it's been evident from some of the things I've been talking about. And I don't know if I'm going to get an answer in my lifetime. One thing I've tried really hard to promote and argue for is that we should at least be open to the idea that we are alone. Often when you hear a lot of popular science astronomers, scientists talk about this on TV shows and things, they'll say, well, of course there's life out there. Of course there is, because there's 100 billion stars in our galaxy. Most of them have planets. And there's 100 billion galaxies. So the numbers are so overwhelming, there has to be. But if you think about it, I would stop there. What do you mean overwhelming? Because that's 10 to the 22 opportunities. But you have to multiply that by the probability of life starting.
By the probability. Yeah, of course.
Yeah. Because if that probability is 10 to the minus 50, then that's it. We're just this like a bizarre fluke in that case. Or if it's 10 to the minus 5, then sure, I agree with you. But I have no reason to think that 10 to the minus 50 is any more or less likely than 10 to the minus 5 right now, because there's this kind of very intangible evidence from our own origins that I've tried to pull apart as much as I can, but even there, it's not conclusive. And then when you add on intelligent life onto that, that's another barrier to cross, of course. So I just think we have to it's completely consistent with everything we know about the universe that this is it. This is the only candle of intelligence in the whole universe. And so I think it's important to be agnostic. I'm not trying to promote that we should think we're alone. I'm not trying to promote that we should think we're surrounded by people, but I'm arguing for objectivity and agnosticism in this question. Because if you do an experiment where you think you know what the answer is before you start, that's dangerous. You're going to get experimenter's bias. The most famous case of that is Percival Lowell. He thought he saw Martian canals on Mars. And for years, it was in the front of the New York Times. Life detected on Mars, Martian canals found. And Lowell just desperately wanted there to be life out there. He was convinced, if you look at his early writings, that of course there has to be life out there by a similar argument. And so he saw what he wanted to see. He saw these very streaks across Mars, which were largely an optical illusion, and interpreted them to be canals. Whereas I think if you saw a streak on a planet now, let's say we had some amazing telescope, you'd say, well, that's interesting. It could be a geological feature. But you wouldn't leap to the assumption that it was a canal system across the planet. He was a product of his time to some degree thinking that. And so we just have to be very consciously agnostic, because so many of us actually want there to be life out there. And there's a lot of religious folks who actually desperately feel the other way as well, really don't conflicts with their belief system for there to be other life out there as well. So there's a huge amount of bias in this question. And so I really, as a scientist, just try to send the message that let's just get the data and see. And I hope we get the answer in my lifetime, but I would be happy if we just do it right and we don't get spurious claims either way.
Cool, yeah. I like that. I like the answer, but scientifically solid answer.
I'd rather have an answer I trust.
Yeah, exactly.
Than a wrong answer. Yeah.
This kind of thinking is, I think, if I remember correctly, formalized in the Drake equation, right? It's like the probability of having life somewhere in the universe. And I find it quite helpful, at least if you're a bit mathematically inclined, because you can really see, since these are multiplications, if you really have, as you were saying, if you have a probability really close to zero, then since it's a multiplication, then that means the total probability is extremely small. That helps you formalize that. And it's something I understood way better when I read that general public book about physics. What was it? We Have No Idea, which is a bit like what you were saying, basically. We Have No Idea by, I think, Daniel Whiteson and Jorge Cham. Really, really cool book. I love it. They also have a podcast called Daniel and Jorge Explain the Universe. I'll put that into the show notes. Yeah, so I got that in their podcast, in their book, The Drake Equation, and that really helps you formalize and see how, well, yeah, it's hard. It's a hard question to ponder. And Also, there is the idea, like the element of timescale, right? Or it's like there is a high chance that we're alone right now, but maybe there were other civilization in the past, or there will be in the future, but we're just not going to be at the same time in the universe and not going to be able to talk to each other because we're not living at the same time span.
Yeah. Well, I would say I just try to push back a little bit on that. I think we could talk to each other. It's not going to be a two-way conversation. And I think a lot of people, when they think of alien life, they expect a dialogue. They expect text messaging each other or something,
which would be cool.
But actually, we talk in a way, or at least we hear from civilizations in the past. The Egyptians with their monuments and the pyramids and things are an effort of communication from the past into the future, one might say. And it's a one-way conversation, but they can still pass a huge amount of information to us. And so I've been thinking a lot about that. What is the purpose behind such communication? Is it to try and teach the future generations not to make the same mistakes they did? That's probably not why the pyramids were made. Or is it some kind of monument to their greatness? Like, remember us, we were here, don't forget about our existence, which I think is more of a selfish reason for that communication. And so that influences what we're doing. I mean, if other civilizations make that same call, they realize, hey, there's no one else out here the same time as us, but there probably will be someone out here at some point. Let's try and be remembered. Let's try and build something or leave something that others would have the best chance of finding. And so that's been affecting at least my thinking a lot about how we conduct the search for life in the universe at the moment.
Yeah, damn. So we have 5 minutes left. So super frustrating. I had tons of other questions, but let's focus on, before I ask you the last two questions I ask everyone at the end of the show, maybe one last question that I think you can answer quite quickly, but about your YouTube channel, because not everybody does that. Not every researcher, right, does the effort of trying to also educate the general public about his or her research topics. So my main question about that would be, why did you decide to do that? Or more precisely, what skills are you trying to instill in people with this project?
Yeah, well, I guess I started because I've always felt passionately about public communication because to some degree, I'm a product of it. I was inspired by scientists who would, like Carl Sagan, who would go up on TV and produce these awesome, inspiring shows, read books about, John Gribb and Schrodinger's cat was a book that really influenced me as a kid about quantum physics. So I think a lot of scientists are a product to some degree or other of science communication. So I wanted to just pay that forward. And I felt that a YouTube channel would have the biggest impact because I was doing public lectures quite often. If you think about that, who goes to a public lecture? They have to, find a babysitter. They have to put the kids to bed. They have to get in the car. They have to drive half an hour somewhere. They have to show up. They have to sit in an uncomfortable seat for an hour, listen to you talk, and then go all the way back again afterwards. That's dedication. And so there's a selection effect, right? The people who come to those talks, you're not convincing anyone to become interested in astronomy. They're already fascinated with astronomy. And I'm not saying that's a worthless activity by no means, but I was sort of more personally interested in trying to affect a broader audience and trying to bring more people under the tent. And so, I started the YouTube channel for that reason, because I thought we could reach potentials billions of people on YouTube. And I think the philosophy of my channel has been to try to make educational videos that speak a little bit to the romanticism of astronomy. I think astronomy has always had this element of this kind of dreamy sense of who are we? Why are we here? What's the human experience?
Yeah, philosophical almost, yeah.
Yeah. And I've tried to blend that into the education because I think I want people to feel something a lot when they watch my videos, even just a little something. And I think that's not how education normally is performed. Normally it's this clinical process. And I just personally think that when you feel something, you're more likely to remember it. It's more likely to make an impact with you. Certainly think about the moments in your life that you most remember. It's probably moments of intense emotion that you felt. And so I kind of try to use that vehicle to try and trick you into learning a little bit with some of my videos. And so when we talk about, for example, the timescale of when the sun will make the earth uninhabitable, there is something kind of tragic about that. And I try to use that feeling to make it more poignant.
Yeah, completely agree. And it's something I'm trying to do also because like the number of people that you encounter, and when you say to people that you're a modeler, or you do math or statistics, like, oh yeah, I know, I hate math or I hate stats, like I like artistic things. I'm like, well, like actually statistical modeling, like astronomy or things like that, actually artistic, I think, because like you have to be extremely creative and inventive, but you have that method that helps you understand whether your creativity is being crap at the moment or is being useful. That's just all. You have a structure, but you can't completely create in that structure. So, and I think it's kind of a problem of how, as you say, like science education is done, which is like not completely outside of the stories and the people which made it. And it's like, just, okay, that's that theorem. That's the proof. Then let's go to that other theorem. And that's the proof. It's like completely outside of, well, the human history that's behind it. And I think it's extremely important to do that because then people realize that, well, it's not something that's just like comes out of the sky and is like extremely rigid and rigorous and without any soul. Definitely that's awesome. And thank you for taking the time and investing in that YouTube channel for all of us.
And one final thing I'd say on that is that it feeds back as well. And I am a better researcher because of it. I communicate more clearly in my papers as a result of it. I speak better, I think, when I give talks. And I've also had lots of wonderful ideas. And I've been pushed into research directions that I would normally would have considered to be out of my lane. I just work on exoplanets. I should only do this. But when I'm doing these papers like The Origin of Life timing, a lot of that was fed by my audience asking those questions and me thinking, yeah, I could probably figure this out actually, and being pushed into new directions as well. So it's a two-way street.
Yeah, exactly. Completely agree. And it's the same for me. Like listeners help me think about new ways of solving a problem, or like they also come to you with new statistical problems, and it's like incredibly valuable. Okay, so like we have 2 minutes left and 2 questions, very fast answers. That's cool. That's the goal. So these questions I ask them at the end of the show to every guest. So as usual, it's the distribution that counts more than any individual answer. So first question, David, if you had unlimited time and resources, and I think you know what you're going to say, which problem would you try to solve?
I think the obvious one would be life in the universe, but I don't know, even with unlimited resources, that's possible. I think just to make it more interesting, the other one I think about a lot and I am passionate about is human exploration of space. And so we're working on a paper right now in my team. We've done one in the past on this topic. It's sort of that almost hobby-esque side projects for us in our team because it's such a hard problem. And it's not the sort of thing that academia normally, let's say, fosters. But we've been working on interstellar propulsion methods in my group and, radical techniques to improve things in terms of our ability to move between the stars. And if I could do anything, I mean, that's when I was a kid, that's what I wanted to do. I wanted to invent a warp drive. I remember clearly thinking that, watching Star Trek and being like, I want to help the world have a warp drive because that looks awesome. And so I don't think we're going to have warp drives, but I do think there is possibility of human exploration of space. So that'd be what I'd like to realize.
Cool. Damn, that's another episode. Maybe with Daniel and Jorge. And second question, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
Oh, man, that's hard. But this would probably change when you ask me this, but I think probably Leonardo da Vinci at the moment, who I know would probably not even fit the standard mold of a scientist, but he was extremely scientific with his work. I've just been reading Walter Isaacson's autobiography of him the last few weeks, and I found it really inspiring. And just as we talked about before, how he blended science and art so fluidly in a way that I think we've forgotten how to do. And he didn't even think of them as distinct things. And so to me, that has been really impactful, learning more about his life. So I'd strongly recommend that book. Anyone wants to get some inspiration in their lives.
Perfect. Definitely going to add that to the show notes and to my own reading list. Awesome. Well, David, I had like gazillion other questions for you, but we are still subject to time in that universe. So we're going to call it a show. As usual, I put resources and a link to your website in the show notes for those who want to dig deeper. Thank you again, David, for taking the time and being on this show.
It was a real pleasure. Thanks so much for having me, and always willing to come back if you want to chat more Bayesian statistics some other time.
Perfect. I'll take you up on that. See you.
Okay, bye.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and subscribe to the show on your favorite podcatcher or on Podchaser, and visit learnbayesstats.com for more resources based on today's topics, as well as access to more episodes that will help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman with MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thanks so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.